Welcome to Zombie Ant Farming, practical tips for playing hide and seek with Linux EDRs. You're in Breakers GHI, here to listen to Dimitry Snezhkov. Before we begin, just a few brief notes. Please stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2. Also, don't forget the Black Hat Arsenal is in the business hall on level 2. Of course, turn off your phones. Welcome, Dimitry.
Thank you, everybody. And I really appreciate you guys coming here. You have choices. Appreciate that. So my name is Dimitry Snezhkov. I am the red team operator for X4Shred. And as part of my work duties, I help my team with tooling, testing, and doing some research. And I'm interested in all things offensive, and this talk is going to be from the perspective of the red team operator. We're going to look at what challenges red team operators have when they evade EDRs on Linux. We're going to talk about the technology. We're going to give you some practical tools, tips, and we're going to release a toolkit that will help you to do the same. But I really want to start with setting the sort of like a context of our talk. We're focusing on Linux because it matters. The reality of today's deployment in data centers, the data, and other things just point us to the fact that Linux runs about 90% of cloud workloads. And no matter what you do, you're probably going to touch, as an attacker, as a red team operator, you're going to touch Linux at some point. The attackers and red team operators that do adversarial emulation, they follow the path to ROI. Essentially, they need to get to data, and a lot of times the data is on Linux. And so we're going to make our focus there. Now, because an attacker ends up on Linux, obviously the defense also follows the attacker, and we've seen the resurgence of endpoint detection and response technology in Linux operating systems, and that's what our focus is. We as operators will have to respond to that challenge. So imagine that you, as an operator, end up being on Linux machine. You drop there and let's say everything is okay. You are not caught. You sit quiet and tight and figure out what's going on. And in 15 minutes, your payload doesn't work. You're evacuated and you're pretty much booted. You're booted out of the system. Your research for what happened starts right there. Was it the EDR? Was it the whitelisting solution that prevented you from doing that? Was it just a mix of deployment, patch management, automation scripts, anything that has to do with DLP, some homegrown automation? Was it manual threat hunting? We do not know. And the state of Linux EDR, state of Linux defense, is a little bit more sporadic, right? We do not know if it's a pure play EDR, if it's something else. So, and obviously we have to contend with that as operators. We have to address our initial foothold mechanisms. We have to figure out the immediate detection capabilities of the defense and try to avoid them. And we have to contend with persistent readiness, right? We need to make sure that we're staying on that box, we're operating on that box, or pivoting out to another machine on the same network while still being persistent there. And lately, we also have to contend with so-called proactive supervision context. What that means is quiet boxes, instrumented operating systems, and whitelisting. And so before we move into specifics, let's talk strategically about what we can do as red team operators to counter that state of affairs. Well, EDRs are sort of very sophisticated piece of software that pretty much do analysis of behavior of system binaries that run in it, and they build a story. They build a story out of the indicators of compromise, and if the story is built, and if the story tells that that's a malware, they shut it down. How can we go against that technology? Well, one thing that we can do is we can actually attack the EDR itself. We can shut it down, we can blindside it, we can affect the operation of EDR itself, we can actually affect the logging or event monitoring of the EDR, right? But that's not the cause, that's not the focus of our talk. The other scenario is to target the execution behavior of the programs that we actually bring on the box. Can we confuse EDRs with our own execution? Can we bypass the EDR detection by pretty much executing commands in a different way? Maybe we can even deflect the artifact discovery when the manual threat hunting is happening, and we can still be persistent on that box. Let's see what we can do. So strategically, we basically need a viable path to build Linux malware in the face of those EDRs. We have to contend with a lot of different things that we do not know on the box. We do not know what they do on the box. You have several choices. Commonly, you can either drop your offensive tools on the target right away. Again, you do not know what's going on with that target. You do not know what you're going against. You may be outright detected the issue of the unknown, right? The second choice is to try to develop your offensive tools right on the box. Well, your mileage may vary because you can have compilers, or you may not have compilers. You may have some form of lockdown box that doesn't allow you to do that. And the third choice is to use whatever is available on the box, so-called principle of utilization. You take what the system gives you and you just work with that. Well, in proactive context, it's very limited, right? And again, you're on the box, you do not know what you're actually seeing there. Now, what if we take a different approach? What if we assemble the attack right on the box? We basically have, all three things that we are talking about. We're living off the land, we are dropping some tooling on the machine, and we're using the facilities of that operating system to go against EDRs. A couple of ideas. The first idea is to bring in instrumented small malware cradles and then build iterative capabilities on top of them. So what are cradles? Cradles are just bootstrap code, just very small piece of software that is not malicious in its intent, but it has capabilities to either grow in its malicious intent or load capabilities into each other or other systems on the machine. And so the second idea is to maybe take the good binaries on a system that is being whitelisted, perhaps, right? Or EDRs have run profile on it, they're deemed to be trusted, and turn them to service our needs, turn them into Trojan horses, into decoys of our malware operations. Those are the two ideas that we're going to explore here. So we're going to talk about two stages. The first stage is we're going to try to build offensive primitives on the box. Those are recipes, tips, and things that will help you to retool directly on the machine. So we're going to use loader, Linux loader and linker in order to do that. We're going to try to see how we can blindside the EDR from behavioral perspective. And we're going to talk about prototyping and rapid iteration of your malware capabilities on the machine. And the second stage is going to be the actual weaponization and operationalization of those offensive capabilities that we build or bring in on the machine. Which means we're going to try to hide from EDRs. We're going to use Preloader as a service. We're going to build it right here and showcase its capabilities. And we're going to try to achieve some form of mimicry on the machine so the EDRs are fooled a little bit more. So let's begin. Stage one, offensive primitives. Before we move into, we have to take a little stroll down the memory lane and talk about the ELF format. ELF format is the executable format on Linux machines. It is much like PE on Windows. It can be instrumented. It runs through a loader, and it has capabilities to load other things in its section. So there are two views. There is a linking section for the executable, and there is an execution view. Some of it is on a disk, the other when you load it into the memory, the linker basically patches the memory locations, does the relocation of the memory, and it starts the process. And ELF is a very interesting format because there are a lot of different interesting sections in it. And we're going to use or make use of them in our efforts here. So from common execution, the loader essentially tries to find libraries that the executable depends on. In common scenario, when you launch an executable on Linux, and if it doesn't find its dependencies, it crashes, it says, I cannot find it. And when you start researching what it is that it's trying to find, you have tools that should be able to tell you that, oh, it's trying to find this library because its linking table is telling it to do so, right? That's where its functionality is, and it cannot find it. And then when the dependency is actually resolved, you can move on with execution of that same program, everything is okay, and you've gained your functionality. So keep that mental picture in mind as we go through that effort that we're trying to make. The other thing about ELVs and execution of programs on Linux is that in order for you to introduce new capability into a binary without having the code is to do so-called hooking of the ELV. Right? It's a very simple thing to do. Essentially, Linux allows you to seek for functionality, for features, for functions, for variables in the locations of the libraries, as well as executables. And depending on the load preference, you should be able to find this function or crash. And if you do find the function in the application elsewhere, outside of the executable, you can hook it. Essentially, you're executing a detour of the function that is being encoded in executable by using your library. That's achieved through the LD preload. It's a feature, it's a facility of the operating system to be able to load dynamic libraries. Now, there are issues with dynamic library loading, right? How do we use this for offensive tools? Well, if you dropped on the box and you need to preload the binary that you want with some of your malware, you have to know the API. In this case, fopen, for example, is a very known API. It's from the LibC. You can preload it pretty easily. But what if you dropped on the box and you're trying to backdoor an executable that you do not know anything about, and you cannot instrument it in any way? So that presents an issue. How do we bypass knowing what that executable does and use it for decoy? So let's move on and see what we can do here. Well, one tip and one idea would be is to try to not understand what that executable does, but just preload it in a generic way. I do not care or should not care what executable I'm targeting to hide my malware. I should take any system executable and be able to preload that. One thing to note is that on Linux you have parent-child relationship, and so if you're the parent of the process you're spawning or starting, then you likely own that process, you likely can introspect that process, and that's your child or parent-child relationship between the two processes. So we can use that relationship to our advantage. Conceptually, from what do we gain for EDR evasion? We load malware into a library, and then we basically instrument it in such a way that it picks up that malware as it loads into the memory. EDRs should be able to lose the trace, should not be able to introspect our binaries, and if they do so, they should not be able to see the entire payload. So we're going to use a scatter and assemble approach for our payload, picking bits and pieces from the payload and assemble them on the box. One curious thing that you may know is that in Linux, because you have parent-child relationship between the processes that you launch, is that it owns resources of the child, right? The parent always knows what the child can do. So what do we actually want? We want to take a target process, a known executable on the box that is whitelisted, and turn it into a malicious executable by various means. One way of doing it is to use sections that are available in ELF, for example, init, fini, and we can build arrays of code if we can bring our own little executables and just preload them with memory with malware. We can compile it in such a way that we can take advantage of those sections in ELF. The curious part about it is that those sections init and fini are executed irrespective of the main of the program, right? They load before the main and they execute after the main is exited. The second tip is we can hook the LibC library itself. LibC library is nothing more than just a set of routines that sets up execution for a Linux process. And so we can dynamically preload an executable by choosing and looking for libc. And we can do it this way, but is it optimal? Notice that we're using a dynamic loading capabilities. We're looking for symbols. Well, EDRs can look for symbols too. They can disable DLSIM and DLOpen. We have to contend with that. The other thing that solves that issue is that we can use weak references. Our compiler allows you to expose functionality, features, and global variables out of your library in such a way that the dynamic loading of that symbol and lookup of that symbol at runtime is not depending on the functionality that you can find. So essentially, if you do not find the function, it doesn't crash the process. If before we were able to load a executable with the library, and if it's missing the library, the process would crash. In this case, we're basically saying, okay, well, can I resolve this debug variable? Can I find this feature or not? If I can't, I'll keep going. Why is it useful? Well, if you're in a sandbox as an operator, you can check for presence of some defensive toolkit and not even load the functionality, even if it's available for you, so EDR does not know where you're loading your malware from. The next iteration of weak refs is that we can find foreign weak refs. If, for example, you're not bringing your malware cradle, but you're actually trying to find the executable on the box to infect. And so you can search for weak references right there. Every executable on Linux pretty much has the two sections, CXA finalize and gmon start. And so you can use any of those to hook, irrespective of what your malware is trying to do. And obviously the chain weak refs allow you to split your payload into two or more libraries. And so when EDR is looking at the memory footprint, it only sees a part of it. One functionality can come from chain 1, the other functionality can come from chain 2. The other thing is that you can actually create pre-constructors of your cradle or executable. Essentially, you're loading a constructor into indiscriminate program, and you say /bin/ls will gain a new constructor which will execute my code as a malware writer. I can be as much generic as I want to. I can even counter the counter to this when EDRs know about that and they say, okay, I'm going to create a generic constructor in order for you, the malware writer, not being able to load it. Well, it turns out that there are priorities to constructors. And so if we take the higher priority on the constructor, we should be able to bypass the EDR. Now, the other tip that you can do is you can actually fool EDR and blind their detection by switching in and out of band of signals. You can send signals to yourself and you execute handlers within the code. And so you basically prevent the EDR to build a consistent flow of logic execution because it's an interrupt. And because it is an interrupt, EDRs do not handle it really well. So essentially you divide by 0, but you recover from it in this case. Right, and that is very useful. And so then you can start protecting your payloads that you're bringing in throughout your libraries that you're trying to instrument. You can remove LD preload from environmental variables. You can do encryption of the memory. You can do situational checks. You can do anything you want if you load it prior to execution with LD load, with constructors, with ELF sections, and so on and so forth. You can even change the loader. LD.so is not the only loader that can load the executables. You can stuff your loader into the section interpreter on the ELF, right? And so if EDRs are instrumenting the loader, they will not see your execution. And so what can we do with this? Let's move a little further. Let's hide from things, right? Like let's expand our foothold. Now, you can use LD, I mentioned LD.so as a loader. You can use that in conjunction with other utilities on the box directly, right? You can bounce off of the LD loader, you can bounce off of the BusyBox executable, and you can basically execute code directly without having any tools on the box. Let's look at the examples of how that's done. Very contrived example, but Essentially, we are chaining execution of the loader to the busy box, and then we're basically saying, okay, well, EDR, chase that, the whole thing. You jump from 3 executables at the same time. Perhaps you escape into VI, which switches the terminal mode, which gives you TTY preferences, and then you switch out of it, execute things. So essentially, the idea is that for us is to break that trust and break that story that EDR is trying to make. Now, there are more things that we can do. We can evade EDR in better ways. We can evade into reflection. What does that mean? Well, some stacks that execute on the box may have its own virtual machines. And for example, if you're switching technical stacks within the same program, you're calling a Go language, you call in Python, maybe you call some other things with common or foreign function interface, then EDR gets confused and it needs to it cannot follow its own chain, right? How do you switch the VM? The representation of the virtual memory addresses is completely different, and so that helps you as well. Let's look at how that's done. Well, you can, your libraries can be preloaded in such a way that you can actually create a contract with FFI, for example, in this case Go. You can invoke its library, and before it gets to main, it has to go through the Go runtime, and digital forensics will have to contend with about 2,000 plus functions to reverse engineer until it actually gets to main execution. So that's very useful. The other thing is you can actually compile statically your interpreter language inside of the library that you're preloading, right? It's very useful because, again, we're switching virtual machines, we're switching how we execute, and we break in the story of things. Just an abstraction level that you can follow. This is another tip for you. So what we've done right now is we've taken an executable /bin/ls, or little tiny sliver of our code, our cradle, our bootstrap. And essentially we create this monster of different things that you can actually do with this executable, right? We do not ask what elf can do for you, but you ask what you can do to that elf, right? And then we can just run with that. Now, in the stage 2, let's talk about weaponization, because this is, while we have all these concepts and tools and tips of how you're going to create your malware, how do you actually weaponize things on the box? Well, the way you can do this is you can start creating your Uber preloaders. We now know that we can actually use LD preload to load our malware, but how do we actually do this? How do we deploy that preloader to the defense, to the target box? Well, executing /bit/ls is really easy, right? We've talked about reloading library before it starts, but how do you account for the fact that ls takes an argument? The argument gets eaten by ls itself, and you should not be able to, do anything useful for it. Well, it turns out that we can actually solve that issue by moving back in our Uber preloader via environmental variables outside of the realm of the executable arguments into environmental variables and taking things from there. So essentially, in this case, we're executing /bin/ls, and we're loading it with, let's say, malware, right? But we also load more things, other module in our malware. And we're basically saying, okay, ls runs, but it gains all this functionality and features from our preloader, right? So we can solve that issue. Now, let's dive deeper into preloaders. Those chains that we're talking about, the chain that basically loads multiple libraries, it can do anything, regular executable can, because you're preloading at the constructor level, you're preloading at the elf level sometimes, or you're loading it in delayed fashion, for example, at a signal that you send to a target executable. Well, you can start cleaning up your stack by basically toggling to FFI, right? The Go link that we're talking about. We can switch IPC mechanisms. We can pipe things in and out of that executable. We're using shared memory. We can use sockets. We can basically create a very elaborate preloader that way. So one small issue with that. As you may notice, we're executing from the disk. So essentially, at some point, you still need to drop some form of an executable or a library into the machine. And that's a problem because the disk is being watched, right? EDRs are saying, well, is this a malware that just ended up being on the box? We talked about proactive execution context where you are basically acquiescing the box and saying, okay, should that executable be there, should it not? That's done on disk, right? So if you drop it, it's an issue. Now, so what's the solution? The solution is to execute everything in memory, right? Well, you can load code in memory and you know, your operating system is going to be really happy. There are facilities to do so. But once you start talking about executing things from memory, this is where your operating system is going to fight you, right? It does not like doing that. So let's make that happen, right? Let's try to overcome that. There are facilities on Linux to execute things from memory. Historically, there have been a few of them. Shared memory through dev SHM. You can also mmap your library into memory space of the process. But as of kernel 3.7, you get a specific system call. A system call 356/319, depending whether you're running 32-bit or 64-bit. And essentially what it does, it basically says, all right, I'm going to map a piece of memory into the memory of the process, right? And I'm going to send you a persistent descriptor, and you can use that descriptor to execute whatever is there. How does this even work? Well, first, you create the descriptor through memfd create, and then you basically run an exec on it. That's not a new technique. It's been used before. But what's valuable here is you're gaining exposure to a proc self file descriptor, right? When you load the things in memory and you're actually getting that, descriptor out. Let's see how we can use that feature or that side effect of execution or mapping the memory through memfd create. Look what happens here. We're taking our Uber preloader that we've created before. We're still executing /bin/ls. We're still using we're still using the modules. We're still using all the facilities of the preloader. But instead of loading the module from disk, in this case is shim.so, you're loading it from a memory location by a descriptor. And the only question that you have to ask, how in the world does this process interact with that descriptor? How does it find it? What is it? How do I actually invoke memory space of a different process? I have boundaries, right? I have to have some relationship to invoke and to find this descriptor in some other memory process here. So let's talk about that a little bit. And before we do that, a little side note, this talk is called zombie ants, zombie ant farming, and the inspiration for this technique actually came from natural phenomenon where there's a species of carpenter ants that get really bad, well, they can get infected by a virus, and that virus essentially what it does, it uses the ant. It's a parasite, and it uses the ant as its host, right? And what it does, it basically compels the ant to go up, climb up the vegetation, bite on a leaf, and then it releases it to die, right? And then so basically the spores fly out, and it starts invading other ants that are in the understory of that forest. The curious part about this whole cycle, is that obviously we do not like killed ants, but the one thing that we like about that is the fact that this specific virus does not kill the ant directly. It does not affect its nervous system. What it does, it actually takes control of the muscles. So essentially you are turning, or cordyceps is turning the ant into a zombie, and then the ant starts climbing just by pure muscle movement. So this is specifically what we're going to do here moving forward. We're going to use the system libraries or binaries as decoys, and we're going to compel them to execute what we want in a more generic fashion. Now, enter zombie ant farm. Zombie ant farm is an out-of-target warehouse and broker for your payloads that runs in a completely different memory space, and it exposes its memory space to processes for interaction. We talked about the proc-fd descriptors, and this is what we're going to do here. It accepts the commands and then basically uses cross-process memory to infect other hosts on the other programs on that host. Let's see how that works. Well, in order for you to do this, you have to understand that, go back to this parent and child relationship in Linux. Your parent can know the child proc system, right? It can introspect the file descriptors. And the child also can refer to the parent back and say, hey parent, what are you running? What descriptors do you have available? So we can use that specific effort in this case. What we're doing is we're taking our ZAF, zombie ant farm, and we're launching it into the memory, and then somehow we get the malware into that process. But the preloader, that Uber preloader that we're targeting, is referencing its parent or any other relationship that it has with the other process to find the descriptors where that malware is located and load it through memfd create. And so what happens is in LD module where it tries to find the malware, instead of going to the disk, it says, hey Zaf, fetch me a malware, and by the way, do not stream the malware to me, but just simply expose where you're storing it. Give me a pointer to your memory space and I'm going to use it. This is what that specific PID is on Linux, and that's how we're able to separate the broker and the payload from the executor. From the EDR perspective, again, we're keeping in the back of our mind is that we have to break the story for the EDR. Now we're working with two processes, and EDR has to make sense of both sides. It has to make sense of the transfer of the payload, the malware between the two processes. It's very hard for them to do at the moment. And so the big picture of ZAF broker is that it launches into the memory. Uber preload asks, go fetch me a payload from elsewhere. It doesn't matter whether it's a network socket anywhere or maybe it's any other memory space, because you can chain them out as well by using the same methods as we've discussed. And by the way, that Uber preloader is going to instrument a victim, right, executable, for example, /bin/ls, to do its bidding, right, to basically do whatever it needs to do. So /bin/ls, a whitelisted executable, gets infected, it gets loaded with malware, and by the way, this malware comes from something that EDR does not see, okay? Now, we can even go one step further. How do we get ZAF on the box? It's also an executable, or it's a dynamic library. How do we deal with this, right? We're playing catch-22. You can't get one binary on the box because it gets detected, to get other binary on the box because it gets detected, and so on and so forth. Well, memfd create is also available for scripting through the, for example, in Python, it's available through form function interface. So you can easily just drop a interpreted script, which is just a piece of text, on any Linux box that has Python support, and you can actually load ZAF itself into the memory by saying, okay, go fetch it from some URL, and all I'm bringing in is just a piece of text, which is my Python script, which is really powerful. And so I called it PyPreload. Essentially what it does, it says, go fetch me a shared object or executable from a remote location. And by the way, as you're starting in, use a decoy. For example, call yourself a bash and execute /bin/ls preloaded with that payload. Okay, so what defense sees is that it sees bash executing little ls without anything external, anything living on the disk, right? Everything is done in memory. So we do not use any bash functionality per se. We're just using it as a decoy, as a mimicry. So it looks good for the threat hunters. And so, the mechanism of loading ZAF is exactly the same. Instead of loading a library from external location, we can use PyPreload as a piece of Python script to load ZAF into the memory, and then it itself will start unraveling the chain of infection for all the executables that you guys want to do. Visual of it is such that, for example, PyPreload goes out and says, load me ZAF, load it into the memory, have a broker into the memory that we can go to and ask for malware. The Uber preloader says, okay, go get me the malware from another location, store it in your memory, give me the process ID, and give me the location, the process descriptor, and I'm going to use to infect other things. So we create this elaborate farm where we're basically generating and trying to work with system executables that are whitelisted or something that is innocuous, and we're trying to basically instrument it in such a way that they are executing what we want, yet EDR does not see that. So let's do a little demo here of that functionality. As we go through the demo, keep this mental picture in mind where the pipe preloader gets Zeph and then it gets loaded into the memory, and then all the things that we've talked about. The first order of business is to fetch the remote binary and execute it from memory. The way you do this, you essentially, let's watch that nothing gets dropped on the box. Then what we can do, we can start the simple HTTP URL server, and then we are basically going to it and fetching the malicious LS through pipe preload that gets LS into the memory. It gets executed. Notice the proc location where it goes from. It executes it in memory. Nothing is dropped on the box on the other screen. So we're running in the memory. LS basically says, I'm good. Now we're going to load the remote library, inject it, and do exactly the same thing. So LD preload, in the regular iteration, it takes a library and basically preloads it into LS, and we can see that. Then we're watching our disk again, and then we're starting again the web server to fetch the payload. In this case, it's a library. We notify pipe preload that's a library. We are notifying what we're going to decoy it as and what we're going to run it, and then maybe we can send some things to LS itself, right, that runs on the box. So essentially, you are executing the preload that gets your malware executed on the box, yet LS actually works and it executes as well. You can kill LS, but you don't have to. And then the other thing is to actually do the same thing with Zeph, that load that broker into the memory and then start unraveling that chain. Let's see how that works here. Same process, starting the HTTP server. We're loading Zeph, specifying that's a binary. We're going to decoy it as bash. Now we have a memory footprint for Zeph. It runs as a process. We can see that it has a socket open to get our commands. We can actually ask for it to load malware. And then we have like a little script that basically says, hey, Zeph, go and get me a malicious LS from elsewhere. And then when we do that, we can actually list the modules that Zeph has in its memory space. And we'll see that LS is loaded as a specific file descriptor, which Zeph is exposing through its memory space. That's memfd create that we're talking about. Okay? And then, so now, instead of executing disk binary, what we're doing, we're executing a specific descriptor that is exposed through Zeph, right? Essentially what we're doing, we're going to its memory process, and we're saying, okay, well, EDR, go try to figure that out. And then the other thing is that we can actually start chaining things. Same thing here, start the server. We still have our memfd with ls. And we're asking to load a library that's not an executable, just a dynamic library that we can do anything with. And it opens up another descriptor, number 7, for example, in Zeph's memory process. And then essentially we are doing LD preload with a proc, just like the executional. In this case, we're actually going one step further, and we're executing system ls with LD preloaded library from remote location. And you can kind of see that there are two modules that are loaded in Zeph, split of functionality, the broker, the executor, the preloader, the binary that we're trying to infect. Okay. So let's go back and let's see what else we can do. Some other thing that that is being researched right now, and we're trying to move the needle further in to counter the EDR detection, is that we can work with with ASLR. ASLR on Linux, basically it says, okay, well, it's address memory space randomization. When libraries loaded from remote location gets launched into the memory process, they get assigned the memory location, and that memory location changes every time the binary is started, right? So anytime you run a binls with preloaded library, that library is going to be at a different memory location. That is the feature of security feature of Linux operating system, of the loader. Now, can we disable ASLR? That's the question. Why would we want to do this? Well, because we can predict memory locations. Why do we need to predict memory locations? Because we can even delay the loading of payloads and exploits into the binaries that we pretty much bring in, like cradles. For example, we bring in a very, very clean cradle, and defer gets the binary, reverse engineers, there is no payload, there is no shared object, there is nothing there, but it has a very curious space of a buffer, for example, 400 bytes, that gets allocated to zeros, and there's nothing going on with it. Now, normally we cannot target that memory location because we do not know what that memory location is at the runtime, because it changes because of ASLR. So what we do is we can weaken the executable. We can actually change its personality by using a flag on set personality call called address no randomize. And because the child and parent relationship still stays, what we do, we fork the process, we change the personality, then we exec the process with the ASLR disabled, and we launch it in memory with a code cave that should be able to receive some form of a write from our third-party process elsewhere. And we do this with a feature called cross-memory attach, right? It's an address-to-address user space write from one process to another. Visually, that looks like this, right? If with ASLR enabled, anytime you launch a process, it gets a different memory space location. But with ASLR disabled, you get exactly the same memory location for the buffer that you're trying to write to, right? And you can do this exactly again with parent and child relationship. The parent forks the child, changes the personality, and then it executes it by overriding its memory space. And then the process VM write is that our preloader or ZEV or anything else that we talked about before, it basically starts writing into the memory space and then populating the victim, which has no ASLR protection anymore, with exploit that we want, right? And then we can use perhaps a signal to jump to a location that we already know to start the execution of the code that we're preloading. So the idea here is to give the red team operators or basically tools to be able to evade EDR, and from EDR technology and defenders to look at how things work so they can actually pick up some ideas and start implementing defense in it. So, what is the offensive summary here? As we can see, the preloading is really, really viable evasion for system executables. Okay, you can bring in a sliver of code, and then you can grow to proportions that EDR will not be able to deal with, at least at the moment. You can even infect any system executable that you can start with all these things that we talked about. You can execute the blended approach by assembling the attack right on the box, but without having potentially compilers, without having all the introspection tools for destination executables that you're trying to infect. You just take a vanilla /bin/ls, top, cd, whatever you want, and do this. We have split the functionality of payload delivery in two memory processes, and we can actually toggle between them, which is really powerful, because now we can do a customer service to malware writers to give me the payload, I'm going to execute it. We do want to use cforum function interface to switch between VM stack and technical stack as we go along to confuse EDRs even further. Defense, please take note. And for the red team operators, even though you have all these tools, do not execute everything. Do not burn your payloads. Do not burn your mechanisms if you do not need to. This is done purely to enhance the security of this space, for EDRs to learn and for you to test that. And then from the malware writers and red team operators, I guess, is that the takeaway is that you need to protect your payloads, and that's one of the ways of doing that. Because if you lose a payload, that means you may lose persistence, you may lose future opportunities to stay in that box. All this code and all the examples, the zombie ant farm and preloader and other things are available at this location on GitHub. It's open source. You guys are welcome to download and play with it. It's also going to be on Twitter if you want to. I can do that as well. And so what can defense do, right? You guys need to start implementing Linux capabilities. BinLS should not be launching sockets. BinLS should not be listening to any IPC. It's not what it's designed to do, so do lock it down. Define clearly what EDRs do for you in this environment. They cannot do everything. It's a great technology, but use it cautiously and augment your efforts with other things. Defense, please provide optics into proc. Please do introspection into dynamic loading. Please watch over IPC, and please provide optics to process library load. This is very, very important because, as you can see, everything is done in memory right now, and unless you do that, you're not going to be able to see this. And then start thinking about quiescing your boxes and doing prevention on things that should not be there. Even a single script, as you've seen, a Python script can bring in the entire thing that will unravel the security of your machine. So with that, I want to thank you for coming here and listening to my talk, and I can take questions.